Okay, we're going to start this video with the problem that uses what we've been learning. So this will just be a good problem to practice what we've been talking about, but also it'd be an experimental way to figure out how strong a magnetic field is. So if you create a magnetic field, but you don't know how strong it is, here's a method that would effectively measure the magnetic field. So we're going to combine an electric field and a magnetic field. So here's an electric field, a uniform electric field, sort of starting here, that goes to the left. And here's a uniform magnetic field. And let's say that we know the electric field well, we can figure out the actual magnitude of the electric field, but let's talk about it in terms of potential. Let's say that from one side to the other is 350 volts difference. So from here to here is 350 volts. Put another way, the right side is higher than the left side by 350 volts. And so if we put an electron on the left side of the electric field, remember, electrons being negatively charged are actually going to want to go uphill. They're going to want to go against the electric field. So they're actually going to go this way. They're going to accelerate. This electron will accelerate. So it'll pick up speed. So if we put it in here at rest, it will have a certain speed by the time it gets to here, and we'll figure that out. So now we'll know its speed at this point. But of course now, as it leaves that electric field, it's got that speed, and nothing's going to slow it down now. So it'll stop accelerating at this point, but it's still moving. And then it'll go into the B field. And of course, once it goes into the B field, the magnetic field, it then goes into a circle. And actually, I drew it the wrong way. It's going to actually go this way. Why is it going to go that way? Well, it's at this point the velocity is going to the right, so your right hand rule is stick your hand out to the right, but then palm forward so that you can curl your fingers forward, and then your thumb is pointing up. But that's the right hand rule. But then this is the first time this is happening in our examples. This is a negatively charged object. This is an electron, so it's all flipped. So actually the force will be directed downward. So this thing will go into a circle downward. All right. And then what you do is you can measure based on where it went in to where it comes out. Maybe you have a screen here that can actually detect like where it comes out, whether it comes out here, down here, or up here. You can figure out the radius. You can figure out the radius of the circle. And let's say we do that, and the radius of the path is measured to be 7.5 centimeters. All right, so we should be able to figure out the strength of the magnetic field from all of this information. So first of all, what is the speed of the electron as it comes out of that electric field? Okay, so the electron has because it's going through a change of potential, it's going to have a change in potential energy. And our old friend delta U equals Q delta V will figure this out for us. So electron is negative 1.60 times 10 to the minus 19 coulombs. It's going up, right? It has a positive change in potential of 350 volts, so that's a positive 350 volts. Put that into your calculator, and I think you're going to get negative 5.60 times 10 to the minus 17 joules. So the electron will lose that many joules of potential energy. But there's no external forces other than what we've written down, right? There's no other force doing work on the electron, so it is not going to lose its energy totally. So if it's losing this much potential energy, that must mean it's gaining that much kinetic energy. Of course, it started with 0 kinetic energy, so any gain is just going to be how much it has. So the final kinetic energy is going to be 5.60 times 10 to the minus 17 joules, right? And so from there, right, we can figure out how fast it's going. Look up the mass of an electron. Let me just fast forward through that algebra, right? Just multiply by 2, divide by m, take the square root. You'll end up getting 1.11 times 10 to the 7th meters per second. So it will have picked up that much speed by going through that electric field. All right, so now that's the V. Now we can switch our attention to, now it's coming out of the electric field and going into the magnetic field and going into this circular, or at least semicircular trajectory, and we can use RQB equals MV. Right, and we have R. We of course know the charge and the mass, and we now have the speed that it's entering the magnetic field at, so we can get B. So B is MV over RQ. And you can plug all the numbers in that we have, and you'll end up getting that it is 8.42 times 10 to the minus 4 Tesla. Okay, so I hope that made sense, and it's a nice connection between electric fields and magnetic fields. You use the electric field to speed it up, and then you use the magnetic field to turn it. And in this case, we didn't know how much magnetic field we had, so basically, based on how sharply it turned, we can deduce how strong the magnetic field was. Okay.